Hi, Matthew.
Can you guys hear me?
Yep, we can hear you. Sounds
Excellent.
great.
Super excited to be here. This was fun. That was a fantastic talk by Roman. And I'm like, Ramon, and I'm like, oh man, this is going to give people whiplash because you're going from macro, microservices, cloud architecture. Now we're going to zoom in on like a single CPU core and how fast can you make that go? So this is going to be a very different take than what we just had. But that
Yeah,
was fantastic.
it is fantastic. It's awesome just to kind of see F sharp and kind of all of the options that you can run it with. So we're excited about this talk.
Yeah, me too.
All right. If you're ready, I'll share your screen and then we'll get out of your way. We'll be
All
here if you
right.
need us, but good luck. The stage is yours.
Much appreciated. See you on the flip side. So my name is Matthew Cruz, and I am incredibly excited to talk to you today about F sharp for performance critical code. I had a joke title for this, which is why F sharp is my favorite imperative procedural programming language, but I didn't think that talk would get accepted. So I didn't use that, but it kind of gives you an idea of where we're going with this talk. Now, to set some context, who am I? I work for a company called Simulation Dynamics. It's a small consultancy that specializes in simulation and optimization of supply chains, warehouses, and manufacturing facilities. And what sets us apart from other consultancies is that our code is all .NET. We typically don't use other types of simulation technologies. And so by having it all be in .NET, it is also extremely fast. Which leads me to the next aspect of me, and that I run a YouTube channel called Fast F Sharp, where all I do is produce content about writing F Sharp code and how to make it run as fast as possible. Now, at work at Simulation Dynamics, we've been working on a project which is creating a new simulation engine, specifically for discrete rate simulation. Now, let me provide you with some context. Typically, simulation exists on a spectrum. There is a huge variety of techniques for doing simulation. On one end, you have discrete event simulation. And kind of what characterizes this is that the change in state over time is either 0 or infinity. And that's because the state is the same and then boom, there's a huge change in state, which also means that the rate at which the state is changing is 0. On the other side of simulation, you have dynamics simulation, so things like weather, fluid flow, heat transfer. And what characterizes this kind of simulation is that the state is always changing. It's never 0. It's never still. Things are always moving, and the rate at which things are moving in that system can be changing. Now, between these two extremes is the idea of discrete rate simulation. And discrete rate simulation has flow in the system. That flow could be material through a pipe, items on a conveyor belt, or people through a training system, or money through investments. But the rate at which things are flowing does not accelerate or decelerate. It's constant. And this technique can be used to model a huge variety of real-world processes, and it's much faster than the other two techniques. So, what were our priorities when designing this new engine from scratch? Well, one of them was that we wanted the development of models to be streamlined, easy, and simple. The speed of model development is critical. We wanted the maintenance of models to be easy. A model is never actually done. As the business changes, the model needs to be changed as well. We wanted deployment we wanted to be able to deploy wherever. We wanted to be able to run it on a client. We wanted to be able to run it on a server. We wanted to be able to run anywhere. And it needed to be fast. If a simulation is slow, it is useless because you need to be making decisions quickly. So the slower your simulation, the longer it takes to make decisions. It has to be fast. Now, the fact that we're building on .NET addresses maintenance and deployment because we can just hook into all the tools that we have for deploying software, pull requests, GitHub actions, automated deployments, all that, because our models are all just .NET code, which leaves us with development and with performance. So let's talk about the development aspect of this real quick. Typically, when it comes to these simulation engines, you are developing in some type of graphical user interface. We are clicking and dragging blocks around and connecting them. Now, that's great at the beginning. It's great as you're like learning a tool, but over time, this becomes really painful because your model development rate is now limited by your clicking, right? And you just click and drag, click and drag, click and connect. It really slows you down. So we didn't want our analysts building models in this way. We wanted a code first solution, which brings us to why F# is great for this. F# has a feature called computation expressions. And what a computation expression allows you to do is to define a domain-specific language so that people could have this kind of declarative syntax for defining a model. And this is fantastic because it's all F# code, but it's code that is in the language of the user. It's code that is in the language of the business expert. And so they're able to look at it and understand it. And this makes sense. Like this is a model of what you just saw on the previous screen. And it's using the words and the vocabulary that the business uses. And so F# is great for this kind of stuff. And there's lots of talks on why people love F# for it. But that's not the point of this talk. This talk is about performance and why, F# is a great language for doing performance critical code. Now, we had some goals for our engine. One of them is that we wanted the user, the analyst, to have a near real-time modeling experience. And what that means for us is that when they make an update to the model, we want the output to be refreshed within 1 second. We want to be able to rerun whatever simulation they were playing with in a single second. So they're able to stay in a kind of flow state and have this kind of experimental experience. And we wanted to do that for a moderately sized simulation. What does that mean? Well, for us, it means 1 million time steps. And so the way the simulation works is you have a moment of time, you evaluate the state of the system, you record some metrics that you will need for doing analysis at the end, move forward in time, reevaluate the state of the system, record metrics, move forward in time. Each of those time steps is the time step that I'm talking about. And we're going to have 1 million of those in a moderately sized simulation. That means we have a time budget for how much time we have at each of these moments. We have 1 microsecond per time step. Now, what first takeaway I want you to have from this talk is that we have a goal in mind. When you're doing performance work, it is critical that you have a finish line for yourself, because it'd be very easy to get caught in this constant loop of like profiling, benchmarking, improving, and like you need to know when you're done. So we've established we have a goal in mind, we have a finish line. Now let's talk about what needs to happen in this microsecond. First of all, we have the recording of the state of the system. And for us, we know that this takes about 300 nanoseconds. We've benchmarked it. We know how long it takes. And this has been pretty well optimized at this point. So 300 nanoseconds. That leaves us with 700 nanoseconds to evaluate the updates to the system and apply them. 700 nanoseconds. Okay, let's see what we got to do. So if you go and look at the literature, you will find this paper. And so if you're looking at discrete-rate simulation, you're going to come across this paper and it's going to say, hey, you should really be using linear programming to evaluate the state of the system. And they give some examples of where that is true. They say like, hey, here's some examples. See, you need to use linear programming. Okay, not arguing with that. So we went and found a really good linear programming solver and we benchmarked it and we found, hey, for the size of simulations we want to run, it takes about 1,500,000 nanoseconds to evaluate the updates for the system. For clarity, our goal is down here, 700 nanoseconds. We are so far off the goal that this is essentially hopeless at this point. So after a few moments of despair, fortunately, SDI was able to give me a few weeks to go and think about this problem. So I go, I read some more literature, I do some investigation, and one of the things I find is like, like that paper was not wrong. But real world problems have distinct features to them, and we can exploit those distinct features. And so we developed a new algorithm for solving the state of the system, and this is where a little bit of proprietary stuff is, so I'm not going to go into that. But that new algorithm requires a topological sort. And if you have those two things, you're able to evaluate the updates. So now let's come back to our time budget. 300 nanoseconds for recording, 400 nanoseconds for this new algorithm that we developed. That's much faster. But you need the topological sort, and we only have 300 nanoseconds in order to compute these topological sorts. So some of you may be slightly confused because I'm using the term topological sort a lot, and I haven't explained what that is. Well, let me unpack that. And you have already experienced these in your life, I guarantee it. Here's an example of a graph. I have a set of nodes, and I have a set of edges connecting those nodes. Now notice that those edges are actually arrows. There's a direction to them. And what a topological sort is, it's an ordering of those nodes so that as you go to each node, you know that you have already visited all the parents. So some valid sorts for this graph would be 1, 2, 3, 4, 5, 6, 7, or 1, 3, 6, 4, 2, 5, 7, and there's several others. So there isn't necessarily a unique topological sorting. Unfortunately for us, we just needed any topological sort for our new algorithm to work correctly. Now, if you go to Wikipedia and look up, okay, topological sort, what are some algorithms for being able to compute those? The first one you're going to come across is the Kahn's algorithm. And Kahn's algorithm is really nice. It's relatively straightforward and simple to understand. And essentially what it does is you start with a node that has no incoming edges. You remove the outgoing edges, and then you check the nodes that you're pointing at and say like, hey, now that I've removed these edges, does this no longer have an incoming edge or not? And if not, then I'm going to add it to the sort. And that's what it's just doing recursively. It's just kind of visiting nodes and like going down. Now, I'm an F-sharper. I'm going to use the most simple domain representation I can think of right off the bat and see where I'm at. So I'm going to have a node. This is an F-sharp record. It has a single field, which is the name. That's a string. What is an edge? It is simply a source node and a target node. I then have sources and targets, which is a map. So I can look up a node and I get all the edges that are incoming or the edges that are outgoing, because the Kahn's algorithm kind of requires you to be able to look up in both directions. And then I have a graph, which is just the sources and the targets. This is my domain. And when I do a naive implementation of the Kahn's algorithm, I'm going to get this result. You might not see anything there on the bottom, but believe it or not, there is a tiny blue sliver. Let me explain this chart real quick. On the vertical axis, we have the throughput. So how many sorts per second are we performing using this algorithm? Our target is here. We need to be able to do 3.3 million sorts per second to reach that performance target of 300 nanoseconds. And we are currently at 0.03 million sorts per second. So we're faster than the linear programming thing, but we're still 2 orders of magnitude off from where we want to be. Now, second lesson I want you to take away from this is that we are measuring, not guessing at our performance, right? So we're using benchmark.net in the background to actually take our code, implement it, and benchmark how fast it is. So lesson 2, measure, don't guess. Now, some of you may say, like, Matthew, your solution is clearly garbage. You're so far off the goal. Like, why do you even give up hope? Clearly, you need to move to a different language. Well, we're not done. We're not done. We're going to go to .trace. I'm going to say, hey, dear .trace, where did I screw up? What am I doing wrong here? And .trace says, this is what you're doing wrong. You're spending a lot of time in this code, which is used for managing F-sharp maps, and sets. Map and set are immutable data structures. Now, I'm going to go on the record and say something that may be a little strange and odd for people, but I believe that F-sharp and mutation are a beautiful thing. F-sharp has no problem with mutation. It loves mutation. What F-sharp does differently than other languages is that it says like you need to be very purposeful about mutation. And I really don't want that mutation to leak outside of context. And so the language has no problem with it. It just wants you to be purposeful about it. It's not the default, but it is possible. And so we're going to use some better collections right off the bat. Like, okay, we don't care about immutable data structures. We need data structures that use mutations so we can go fast. And so instead of set and map, we're going to move to using hash sets and dictionaries. Okay, here's my mutable domain now. I still have node and edge. Nothing has changed. But sources and targets are now using a dictionary instead of a map. I'm going to have a faster lookup using the dictionaries than I would have had using the map. And graph hasn't changed. I benchmark this. I'm at 0.1 million sorts per second. I'm 4 times faster, but I'm still a long way off. Fortunately, the talk is not over. But third lesson, using the right collection for your use case will dramatically improve the performance of your algorithm. I mean, this is pretty obvious, but I think it's still important to repeat this because, you know, the fundamentals of performance are like, are you using the right data structure? So using a fast data structure for our use case, we get faster. Yay. We're still not where we need to go though. So we're going to go to .trace. Dear .trace, what am I doing wrong? .trace is going to say, hey, Matthew, you're spending a lot of time on hashing. Like, why is my algorithm spending so much time on hashing? Excellent question. We need to talk about F-sharp's equality and hashing defaults. Now, F-sharp types have structural equality so that when you compare two values of the same type, it's not going to compare the references. It's actually going to compare like what's in there. And so I have a simple chicken type. I use farm animals for like all of my type examples. So you're going to see a lot of animals in this talk. So I have this type chicken. It's an F-sharp record. Single field of name. This is a reference type. It's allocated on the heap. I create A chicken. I create B chicken. Different references. Same internal value. Are these chickens the same? In a lot of languages, they would not be the same. They have different references. They're pointing to different places in memory. But F-sharp has structural equality. So F-sharp would say, yes, these are the same. This default is super useful as a former analyst. Like when I was doing all kinds of analysis work, this is the way my mind thought. This is why F-sharp clicked for me as a language, because I had a hard time with reference equality. But this default behavior is not the fastest thing ever. I'm not saying it's wrong. I'm just saying it's like, because it has to be robust and deal with every possible scenario, it's not the fastest code you could possibly write. It's not a fault of language. It's just a reality of what we got going on. So, question, what has fast equality and fast hashing? The lowly integer. There is nothing faster when it comes to equality or hashing, because equality for an integer is a single CPU instruction, and hashing for an integer in .NET is nothing. It's just the integer. There is no hash. So it's instantaneous. Now, the problem when we use integers for everything is that a raw integer has no context about what it's meant to represent. I do not like that. And I have dyslexia. So keeping track of like all these integers and what they're meant to represent can be really difficult for me. So I like to use the feature in F-sharp, which is units of measure, which allows us to add context to the primitives of F-sharp. And here I'm defining 2 units of measure, meter and second. And what I can do with this is that I'm going to annotate some floats and say like, hey, D is 10, but it's 10 meters. And T is 2.7 seconds. I'm adding domain context to these primitives. Now, the great thing about this is just a compiler check. This all gets erased when it goes to compiling. So this is a true zero cost abstraction over your code. There is no performance penalty for this. And what's great is that now the compiler can check your math for you. So you're like, hey, this doesn't make sense. And if you hover over it, you're going to get this error message saying, hey, the unit of second does not match the unit of meter. And we are going to utilize this feature quite a bit. So I'm going to change my domain. You see like, hey, the units are off. I'm going to change my domain to utilize units of measure. And what I like to do is I like to have a module in F# where I put all the units I'm going to use for my project. And then I'm going to define the node type and the edge type. Now, node is now just an integer, but it's not a naked integer. We've added domain context. Like this integer is meant to represent a node in our domain. And edge is an int64. And the way we're doing it is we're saying the top 32 bits are the source node and the bottom 32 bits are the target node. And the reason I want that as an int64 instead of like a struct with like two fields is like, again, I want that stupid fast hashing inequality. And so I'm just like, hey, just use an int64. Sources and targets and graph have not changed. It's just those underlying types have changed. And when I benchmark this code, I'm now at 0.19 million sorts per second. Better, not great, but this actually enables a lot of other things that we're going to do later on. And the lesson I want you to take away from this is use a minimal data representation of your domain. Like strip it down to like the simplest bits if you really care about performance, because these added layers of abstraction are going to slow you down. But F# has units of measure, so you're still able to add that domain representation to these primitives. Again, I go back to .trace. Dear .trace, what am I doing wrong? And it says, Matthew, this toList is really expensive. We need to kind of talk about, okay, what is slowing us down here with this toList? Like, what is going on? Now, fortunately, we've been using benchmark.net for all these benchmarks. And benchmark.net has this amazing feature, which is hardware counters. As the CPU is running, it is reporting metrics on what is happening. And some of the things it reports on is like, hey, there's a cache miss. I needed some data. It wasn't in my cache. I had to go out to main memory. Or things like, hey, there's a branch in the code. I predicted one way, but I was wrong. And so there's a branch misprediction. These are great things to look at to say like, hey, how CPU friendly is my algorithm? Because if you have lots of cache misses, it's going to absolutely murder your performance. It's going to be absolutely terrible because going out to main memory is over 100 times slower than accessing something that is in your cache. And so we want to get these cache misses down. The list type that I talked about before, that's a linked list. Linked lists are fine. They are useful for some scenarios, but they are possibly the most performance antagonistic collection that you can think of because each element of a linked list could be allocated anywhere on the heap. And so the CPU is going to have a really hard time figuring out what data needs to be brought in for me to work on. So we want to move to a collection that has better data locality and is more cache friendly. What is the most cache friendly collection that exists? Well, the humble array. It's just a continuous block of memory. It is very easy for a CPU to like look at that, say like, oh, I need this whole chunk. Boom, like put that all in cache. Very simple for it to use. The problem with arrays is that if you have a lot of them floating around that you're working with, and you have all these integers used to indexing into those arrays, it's really, really easy to index into an array with a wrong integer as your index. And again, with my dyslexia, it's really easy for me to lose track. And so I would like a way to provide some domain correctness to my array access. And the way I'm going to do that is with a couple of collections, row and bar. What are row and bar? These are structs. They wrap an array, and they enforce the use of units of measure on your indexing int. So when you go to get a value out of the array, that integer can't just be a raw integer. That integer has to be decorated with a unit of measure that data is intended to be indexed with. And note, the performance of row and bar through the magic of inlining is exactly the same as array, because essentially like they're kind of getting inlined and erased at the end of the day. Now let's look at how you would end up using these things. I have another measure, which is a cow. And I'm going to create a row. A row is a read or write wrapper of the array. Bar is a read-only wrapper of an array. They both enforce the units of measure on the indexing int. I'm creating this row. I say like, hey, I want to create a new row with a default value. I want to have 10 elements in this array, that backing array. The indexing int needs to have the unit of cow on it, and the default value is going to be 0. So now if I want to index into that row, that indexing variable needs to have a unit of measure on it. And so here, 0cal_index is an int with the correct unit of measure. And so I'm allowed to index into that row. But if I try to index with a raw int, the compiler is going to say, no, this doesn't make sense. Like, you need to have the correct unit of measure on it. So this is a way for us to provide additional domain context to our data and how it's laid out and how it relates to one another, all with, just raw primitives, but units of measure for safety. So let's talk about what this array-based implementation of our domain looks like now. We still have our units. Node and edge have not changed, but now sources and targets are going to be a bar instead of a dictionary, and a bar is the read-only wrapper of an array. And instead of pointing to lists, it now points to an edge array. And graph has stayed the same. And when we benchmark this, we're now at 0.4 million sorts per second. We're making progress. We're getting there. And the lesson I want you to take away from here is that the memory layout of your code is critical. If your collections are difficult for the CPU to reason about, their performance will suffer. So the simpler the collection, the happier the CPU. Dear.trace, what have I done wrong? It's saying, yeah, you're spending a lot of time doing this hash set stuff. You should do something about that. So the question I have for myself is like, where is this hash set? And here's the code for the algorithm, or just a chunk of it. And we're using this hash set to keep track of which edges are still in the graph. If you remember at the beginning, the cons algorithm works by going to a node, removing edges, and then checking the nodes that those edges were pointing to and saying like, hey, does this node no longer have any incoming edges? And we're using this hash set to keep track of what edges are still in the set. Okay, well, why would a hash set be slow? And I'm putting air quotes around it because hash sets aren't actually slow, but like, let's look at the work that they're doing. So what does a hash set have to do? When you give it a value, it's got to generate a hash for it. It's got to perform a random array lookup to whatever that hash maps to. It's got to see, is there an item in this bucket or not? And is that item equal to the thing I'm checking to say if it's actually in the hash set or not? That's a lot of work. So the question is there something that would be faster for this type of scenario? Like if, okay, I want to be able to like look something up and say, is this true or false? Well, yeah, there is. It's a bit array. Bit arrays are stupid fast because it's just an array of bits. You can go like, hey, what is the value of this bit? Is it 0, 1? And in our case, we can map our edges to a bit array. Now, I'm aware of the bit array in .NET. It did not have the API that we needed for our scenario, so I had to create something else. And so what I did is I defined a bit set. And the bit set is just a wrapper around an array of bits. And again, I'm using the units of measure. If you want to index into this thing, that indexing int has to have the correct unit of measure so that it makes sense for my domain. And so we're going to enforce this up front. I think the API behind this is actually pretty straightforward. I mean, we're doing some bit masking and bit shifting to say like, is this thing in there or not? But it's essentially the same thing as a bit array, but with additional checks for the domain correctness. And when we swap out the hash set for the bit set, we're now at 0.8 million sorts per second. And what we're seeing is that, hey, our cache misses have gone down and our branch mispredictions have gone down. And that's because a bit set has a simpler set of instructions for doing what it does compared to the hash set. And so what I'm wanting you to take away from this is like we're hitting on the minimal data representation idea. Like we're distilling our problem down to like, what are like the truly essential bits of data that we need to work with? I come back to .trace. What am I doing wrong, dear .trace? And it's like, hey, you're spending a lot of time on the stuff like adding and removing things from a queue and a stack. Now, with the cons algorithm, you need to keep track of like what nodes you're working on and what nodes you already have sorted. And we've been using a stack and a queue to be able to do that. Now, these collections are being allocated on the heap. And as we add elements to them, they periodically have to grow. Now, normally that's amateurized, but like we're calling this thing again and again and again. So we're creating a lot of collections on the heap for the GC to deal with. and we're having to resize them a lot because they're always starting small. I know I could create them with an initial capacity, but I just don't want to allocate on the heap at all. So what I'm going to do is I'm going to use some stack allocation in F#. Yes, F# loves it, some stack allocation. Who needs the heap? And what we're going to do is we're going to create a little collection called a stack, which basically provides a stack-like API over a span of data. And so instead of using stacks and queues allocated on the heap, we're just like, no, we like our stack allocated stuff. Now, caveat, there are some, using the stack, you have to be careful. So don't be aware of the limitations. I don't have time to go into them, but I'm telling you, like, there's more to it than this because the stack is a limited resource. But for our domain, we know that we will never allocate that much space on the stack. So it's okay. We benchmark this. What do we see? 1 million sorts per second. All right, making progress. And again, I want to harp on the fact like your memory layout is critical. When you allocate on the stack, you're essentially guaranteed that that memory is going to be in the cache because that is like the active memory that the CPU is working on. And so stack allocated stuff is stupid fast because 0% chance that stuff is actually out in memory. Okay, come back to dot trace. Teach me your ways. And at this point, I'm going to be honest with you. Dot trace isn't showing me anything. It's like, yeah, your code's fast, bro. Okay, well, that's a problem because I still need to go faster. And I've used other benchmarking tools, but yeah, they all kind of get to the same point. Just like, yeah, your algorithm's running. You're spending all your time in your algorithm. I'm like, that's fantastic. Thanks. So we need to go back to our benchmarks. And that's like universal across all profilers. That's not a thing with just dot trace. That's everyone, right? I look at my benchmarks and I say like, okay, what am I doing to the CPU? And I see, okay, I'm still got a lot of cache misses going on. I still have a lot of branch mispredictions. What's going on? And so at this point, we should ask ourselves like, okay, how is our data laid out in memory? And right now what we do is we have sources, and sources is a bar. It's a read-only wrapper on an array. And inside of that array are references to other arrays that are on the heap. These arrays could be spread all over the place. That is not so good for the CPU because the CPU is going to have to like follow this reference and then go see like, hey, is that thing in memory or not? Is there a more cache-friendly way of laying out this data? And there is. It's a compressed format. And if any of you have done sparse linear algebra, there's this idea of the compressed sparse row format. This is going to be kind of like that. If you don't know what that is, it's not a big deal. I'm going to walk you through it. We got it. So I'm going to define a new unit of measure, which is index. I got a new type, which is index. It's an int with a unit of measure of index. And I'm going to define a new struct, which is a range. And it's going to have a start index and a length index. And a range you could think of as a span, except instead of pointing to somewhere in memory, it's meant for indexing over an array. And now instead of having sources and ranges, I have source ranges, source edges, target ranges, target edges. Okay, let's talk about like how we would work with this now. So if I want to look up the target edges for node 0, what would I do? I would go to source ranges. I would look up that first value, and that would have a range in it, and that range would have two different indexes, a start and a length. I would then go to source edges and say, hey, this range is telling me to look at item 0 and for a length of 2. Those are the edges that I care about for node 0. Why would we want to go through this kind of rigmarole to do it this way? Well, now we are working with only 4 arrays for our graph instead of 2 for every node. This is going to be much easier for the CPU to reason about like, okay, what data do I need? It's like, well, okay, there's only 4 arrays. I guess I need those 4. Like, that's it. It's not having to go running around looking for all kinds of arrays all over the place. So when we benchmark that, it's like, oh, awesome. 1.4 million sorts per second. We are making progress. And our cache misses have gone down significantly. Our branch mispredictions have gone down significantly. So a repeat of lesson 5, memory layout is critical for performance. Now, at this point, we kind of do some introspection. We go look at our algorithm. And this is where I'm going to give you a freebie lesson. I didn't really include it in the outline at the end, but academic descriptions of algorithms are just that, an academic description of an algorithm. It is not an engineering solution. Those are wildly different things. And when I implemented this initially, I just did the naive implementation, basically kind of copying and pasting the academic description of this. And that's not me disparaging academic literature, not at all. But that explains the need for a software engineer to kind of look at that and think of it as a spec. And then like, okay, how am I going to implement the spec? And when I come back and look at this code, I'm like, okay, I got these two different lists I'm supposed to be tracking. I'm using stack allocated memory, but like, wait a minute. At the end of the day, all of these elements are all ending up in that final array, that final collection. So do I even need to put them in this intermediate list called S in the cons algorithm? No, we don't. We're going to go to a solution where we're only going to use one array instead of two. And in this array, we're going to use two different indexes. One index is going to say, hey, this is the next node you need to process. And the second index says, okay, if you need to add a node to this sort, this is where you're going to add it. And so these two kind of indexes are going to kind of, move along as the cons algorithm progresses. The point being, instead of working with two arrays, we're working with one for our result. And when we benchmark that, we get another small boost in performance, 1.6 million. The second refinement to this algorithm comes when we look at edges. Like, okay, why are we using edges here? The reason we're tracking edges is because we want to know for a node, have we already visited all of its parents? Have all the incoming edges for a node been removed? That's why we're tracking edges. Is there another way to track whether all the parents for a node have already been visited or not that doesn't involve edges? Maybe. Well, if we look at source ranges, that length that's in there tells you, okay, how many edges are like pointing at a particular node. Instead of tracking edges, what if we just track the count? So that when we visit a parent, we go to the children and decrement like the number of incoming edges. Like, hey, I visited a parent for this node. Decrement, it's like source count. And when that counter reaches 0, that would indicate like I visited all the parents. Okay, well, that means we don't really need edges. And if we don't need edges, why not just store the nodes here for source edges and target edges? Because we're not using edges anymore. We're just using counts. And so we're going to change the way we represent our domain to say, hey, we now have source nodes instead of source edges and target nodes instead of target edges. And this is going to change our algorithm a little bit. So before, we'd have to remove the edge. We'd have to check if all the incoming edges have been removed. And if it had, then we add the node if all the parents have been visited. Instead of that, our code's going to look like this. We're saying, like, hey, we're going to decrement the source count whenever we visit a parent. And when that count goes to 0, we know we have visited all the parents because we only visit nodes once in this algorithm. And when that happens, we're going to add the node to the result array. And so when we get rid of edges and we're using counts instead of like tracking the edges, we're now at 2.9 million sorts per second. Fantastic. We still got a gap, but we've gotten a lot closer. And again, this is a repeat of lesson 4. It's that minimal data representation. It's the idea of like, okay, do I actually need all this data to do this work at the end of the day? Like, I didn't need edges. I just needed the nodes, and I didn't need to keep track of what edges were in there. I just needed to keep track of counts. It's a simplification. Now, this gap still exists. And I'm going to be honest with you, a month goes by. I don't make progress on it. I ask lots of questions. I'm trying all the things. I'm not finding anything. And then fortunately, I come across this guy, Fedor Pikus. Fedor Pikus is a C++ developer extraordinaire, and he has some incredible talks from CPPCon, and one of them was on branchless programming. Now, if you remember, I've mentioned branching and branch misprediction. When a CPU is running, it is having to prepare work for the thing that actually does the job. And when it comes to a branch in code, it has to guess which way you're going to go. And it guesses and then sends a bunch of work down the line. But then by the time that branch actually gets evaluated, if it guessed wrong, all the work that it has already done has to get dumped. And it goes back to the branch and goes down a new way. Those branch mispredictions are very painful. Now, CPUs are incredible pieces of engineering that are very good at predicting, but if we can help it, it will be happy. Now, if you try to do this in F#, this branchless code idea, and this is kind of a simple idea of like something you would do in C, C++ for branchless programming. Like I have some value, I have A, I have B. If A equals B, then I want to like increment some value. But F# is going to be like, no, you can't do this because A equals B is a bool. You can't add a bool to an int. And F# like plays it safe. It doesn't have the simplistic casting stuff, none of that. So it wants you to do something like this. We're like, hey, if A equals B, then 1, else 0. Like, well, this is the very definition of a branch. And we do not want this in our code. This is bad. That's not bad. For performance, this is less than ideal. Fortunately, Don Syme left a cheat code inside of F#. Danger ahead. But it's there. It will compile. And it's never coming out. And it's the idea of you could inline IL in F#. What is IL? Not everyone might not know that, but when you take C#, VB, or F# and you compile it, it actually gets turned into IL, which is an intermediate language. The .NET runtime then takes that intermediate language and maps it down to the actual hardware architecture it's running on. IL is it's a different beast in terms of programming languages, and there's a reason you don't write in it. But it allows you to do silly things like this. So I am going to use some IL. I have to use this no warn at the top of my code. Otherwise, the compiler is going to complain and send a warning saying, like, hey, you're inlining IL. And I'm like, bro, F#, I got it, don't worry. And I define this function, which is retype, which is incredibly unsafe. And it says like, hey, whatever type this is coming in, look at the code, look at where you use it and just like recast it for me. It's all good. Trust me. And so that code we had before, which wouldn't work, at the end there, instead of just A equals B, I have retype A equals B. And then when I go to use it, I say, the compiler's like, oh, okay, Matthew, I got you. Like A equals B, I know that's a bool, but you're telling me to retype and you need it to be an int later. I got you. I'll just cast it for you. Don't worry about it. So this is how you can start doing some silly branchless coding stuff in F#. Now, some of you may be horrified. Don't worry. This is a very small piece of our code base. It's very isolated. There's lots of testing around it, like all the proper safety precautions that have been taken. So don't think that I do this all the time. It's only when the performance requirements require it. So compiler's now casting to an int. Everything's happy. So we're going to take this branchy code on the left, and we want to get rid of this branch. And so what we do is, hey, no matter what, we're actually going to write this node ID out to the result array, but we're only actually going to increment the count when that source counts equals 0. And that count is what's telling our algorithm, like, hey, how many nodes have you to process or not? So we're always going to put it in, but we're only going to update that increment when it is appropriate. So this gets rid of our branching code. And when we when we benchmark this, we're now at 3.8 million sorts per second. So the takeaway from this is make algorithms predictable. You don't always need to use branchless programming to do it, but if you need to, you can reach for it. So what does this mean for real world performance? Like, Matthew, you spent a lot of time in this topological sort algorithm, but like, you don't get paid for topological sorts, you get paid for simulations. I'm like, dang straight I do. So we went and benchmarked this thing against a industry standard engine. I'm not going to say which one. People complain when benchmarks don't make them look good, but we took a model, we simulated it for a full year, and it takes 132 seconds. Using our engine, which is called IDOS, it takes 1 second. So this is game changing in terms of what you can do with simulation, because now at over 100 times faster, we can start doing optimization. We can start doing machine learning on the results. We are enabling capabilities that would never have been conceivable before. So what I want you to take away from this talk. Well, first of all, F# is a simple, succinct, and fast multi-paradigm language. It is not really a functional language. It has functional features, but it is not functional only. When you do this performance work, you need to have a finish line in mind. You want to measure. Don't guess at what your performance is. Have the right collection for the job that you're doing. Use a minimal domain representation for your problem. Memory layout is critical for performance, and make your algorithms predictable. Your CPU will be happy. Units of measure, add domain correctness for high performance code when you're dealing with just the raw primitives. F# has productive and safe defaults, but it leaves the door open for optimization. Yes. So thank you to the community. F#, here's several people, Jeremy, Denis, and Martin, answered a lot of my questions on Twitter and the F# Slack. They were incredibly helpful. Thank you to JetBrains for having me today. It's been a real delight to share with you. If you like this, you want more, check out my YouTube channel, Fast F#. This is all I do all day. It's just how to write Fast F# code. So thank you all very much for having me.
Yeah, that was awesome. I was kind of rooting for you. Like, I'm about to just cancel all my Netflix subscription and just watch the story kind of unfold when it comes to that chart.
Yeah.
You started nothing, and now you beat it. It was yay, and everyone in the chat was cheering for you. So that was just an awesome talk.
Yeah. Well, thank you so much. Really appreciate it.
Yeah. But yeah, Martin Baliao, our JetBrains compatriot, he said this is evil, but then he followed it up with good evil.
It's kind of evil we like.
Yeah, I love it.
So one of the things folks were asking, how long did this take? You said there was a 1 month span in there, but
yeah.
How long was this journey? Because we took it in an hour, but obviously it didn't take you an hour.
Yeah. So to be honest, there's effort hours, and then there's learning time, right? Mm-hmm. So in terms of the everything up to the branchless, that was probably 2 or 3 days, right? And that was just this really rapid iteration loop with .trace, which is incredibly helpful because it's okay, what am I doing wrong? And there's some things I knew were likely candidates just based off of previous work, but I wanted to start with naive and then progress from there. Mm-hmm. In part to just also kind of illustrate to people yeah, this is what you would do naively, and there's nothing wrong with it. And that's why you need to have that goal, because hey, maybe the performance with that completely naive solution was good enough. And then okay, well, you can stop now. So 2 or 3 days for all those first few iterations, because it was relatively clear. And I have experience with the compressed sparse row format stuff. Again, my previous life is an analyst, mm-hmm. and applied, I'm not a real developer. So I knew of that stuff ahead of time. The branchless stuff, a month goes by. And what I mean by that, I'm absorbing C++ talks, I'm reading C stuff, and I was also just working on other features of the engine, mm-hmm. right? Because the engine is more than just a topological sort. There's a lot of other things that need to happen, and the performance was close enough that we could still go to market with what we had. Mm-hmm. It just wasn't reaching that ideal, and so for me, once I kind of grab onto a goal, I'm I am not letting this go. So my work was actually super happy. SDI is just Matthew, this is fantastic. And I'm it's not good enough.
Yeah, I mean, I guess the follow-up question to that is you were showing your benchmark.net. It's clear, mm-hmm. Just from all these talks, how much benchmark.net is kind of the backbone of performance tuning.
Oh yeah.
Of .net. But was there ever a time you didn't make progress? You actually fell back as you were kind of exploring ideas?
Yeah, no, that's a fantastic question. And I could have an entire other talk, which is like where I'm at right now, like all the things that I've iterated off of where I'm at this moment. Because for kicks and giggles, I would like to go even faster, just as like as a challenge to myself. Again, my work is very happy. I'm not getting any pressure from them. But all the things I've tried to do is sort of like, oh, I'm going to go raw pointers. I'm like, oh, I'm going to use like the pinned object heap, right? Like all these other things for like, hey, and I've also tried like, hey, and have the graph just be like one block, like one array, and then just like take spans off of that and kind of cast it to whatever it is that you know it is underneath the hood. And so none of that is helping. Everything is slowing it down. And that kind of goes to testify to how good .NET is at eliding bounds checks and all those things that I don't want to flame anybody. But there are certain programming language communities which say like you can't do real work in .NET because, you know, bounds checking and garbage collection and all that. The reality is, I have found in my experience, well-formatted code erases all that stuff. So if you look at, and I didn't go and like show you like the x86 assembly that's being generated here and like what's like deeply happening underneath the hood, like all that stuff's getting erased. So all those things that certain other development communities would say like, oh, you can't do real work in .NET. It's like that stuff all gets erased at the end of the day. So you, when you try those tricks to get more performance, you're actually like making it harder for the CLR to figure out what you're doing. And so now it's like not able to do the optimizations it was doing for you before. And so it's one of those things like there comes this point to where, hey, your code is clear, your code is concise, and the CLR is able to reason a lot about it. Like, just step back, man. It's okay. It's cool. And I'm actually actively learning C to re-implement this in C just to see like how much is left on the table in terms of like, okay, if you have a raw C implementation and this F# implementation, like how much are you actually giving up? Is it 10%? Is it 50%? Because if it's not an order of magnitude, if it's not like twice as fast, like we're not enabling any more business use cases for us. And that for us is the critical thing. Like if there's something you could do to move the performance an order of magnitude, now you're enabling new use cases for the business that would never have been conceivable before. And so that has been like our big push for the 1 second simulation run, because as an analyst, you're very used to like setting up a simulation and then like walking away for 10 minutes as that simulation runs, because those engines are designed for flexibility, not necessarily for performance.
Yeah, I was going to ask, like, from a like, have you looked at other languages like C, Rust, Go, those kind of things? But you answered that question. So
yeah, and probably the one that I'd be most interested in implementing this in is Odin, which is another one of those successor to C languages. And it's because Odin has a lot of the things about it. Like it has a lot of the F# features that I really like. And so like the paradigm shift for me would not be that difficult. I don't, oh man, I hope no one throws stones, but like, I don't care that F# is functional. I do not give an F about monads.
No.
Yeah,
Oh,
but because at the end, yeah, because the reason I love F# is because it lets me get my work done fast and correctly. And it's, yeah, and it's just kind of like, I learned F# to get a job done. Like the first thing I ever wrote in F# was a simulated annealing algorithm for graduate school. And like, and it was just because the units of measure saved my bacon. And then like before that, I was developing financial trading algorithms, and units of measure errors are very expensive when you're dealing with billions of dollars. And so those units of measure are incredibly valuable.
Yeah,
Might have to bleep that out later.
Husk is in the chat, so I wonder if I think he's just fallen over. I think.
Sorry, Jet.
Rachel, do you have any specific questions?
Yeah, there's some more. Good one was about how much hardware affects the numbers. Have you noticed if you swapped out hardware? What are you seeing there? Any patterns? Any good takeaways?
Yeah, no, that's fantastic. And fortunately, so the people I mentioned there at the enemy, specifically Denis and Matan, they were running it on their machines. I think Denis was running it on a M1, and Matan was running it on an Intel. I work on a Zen 2, right? And so I know some specific things about the architecture I'm working on. I really only care about x86 performance, because that's what we deploy to. Mm-hmm. But the Apple M1 is crazy how fast that was. And part of it has to do with just the memory bandwidth of that chip is so phenomenal. And just, I noticed cache sizes are for this code really critical, because at the end of the day, the instructions are so simple. It's just like, hey, can I keep that working set in memory all the time? So will you get different performance in different chips? Yes, but the overall scaling kind of remains the same. So the best version, that branchless version, was the best across all chips, right? It's only when I started doing those wacky things at the end that I was talking about that, like, then performance started doing all kinds of bizarre things. That's just because the runtime is like, what are you even doing?
Yeah,
I get that a lot.
Yeah.
Yeah, I wondered, like, just could you crank the gigahertz and just kind of call it a day, and
there's always that one person, usually in management, and they just want to throw money at the problem, which means buy more hardware. Yeah. And that's really not a great strategy.
Yeah, no, completely agreed. And one thing I didn't touch on here is that parallelization is not helpful for this. Parallelization actually hurts it, because when you're doing simulation, and if you have multiple cores, what you would rather do is just spin up a simulation per core, right? Because you're likely wanting to explore different scenarios. And so, like, trying to take this algorithm and like spread it across the CPUs, again, would just be atrocious because of just in cache invalidations and stuff like that. And so that's where I very specifically focus on, okay, single core performance, because that is our use case. And it kind of goes to Ramon's talk where he talked about the resources. Like, hey, what are the resources that you're using? If your code takes 1/10 of the time, that's 1/10 of the compute time. That's a lot of money, a lot of money. And this is a few days worth of effort in like optimizing this algorithm.
Wow. My brain's spinning. I'm gonna probably rewatch this talk just to kind of absorb it all. Rachel, do you have any last questions?
Yeah, certainly. Well, there's a lot of good stuff in here to explore. Now, you did some domain modeling here with F#, and it is pretty amenable to that sort of thing. But have you found other languages or a problem that isn't a good fit for F#? Because you did mention that it's, gasp, not necessarily functional. Everybody flocks to it for that generally, but it does have an all-purpose way of being able to use it. So is there something that doesn't work well for modeling?
Ooh, so I would say there's something that's unintuitive, right? You said, so like F# is definitely the defaults kind of impel you toward this kind of domain modeling and functional programming as a key. Oh man, how do I stay out of trouble?
You don't, just let it rip.
Yeah. Well, so again, I'm very focused on a very specific niche, which is simulation, optimization, large scale system simulation. And so most of the inspiration I take is from games, video game engines. And they have a lot of them. There's a lot of hype around the idea of like entity component systems. And initially, when I started writing the simulation, I was using a very, what would be considered kind of F# idiomatic way of making things with records and DUs and all that. And that's still all great. That form of composition does not scale for performance. It doesn't. If someone can do it, I'd be heck impressed. The ROC, R-O-C, ROC programming language is doing some really interesting stuff in terms of pushing the performance of a purely functional language, but also being as fast as like C. Richard Feldman has a great talk on it. But we're talking about F sharp. F sharp with the use of units of measure makes it really easy and straightforward to model things using an entity component system style of design. And so our engine, IDOS, looks more like a game engine than anything else. It has some slightly different rules because it's not doing like time deltas and interpolation and stuff. But if you look at it, like this is kind of laid out like a game engine. And the use of rows and bars for wrapping arrays allows you to have that domain correctness of access, but the raw performance of just, hey, I'm just indexing into an array all over the place. But that was not an intuitive place to go, right? Like that is not what the F sharp literature would like impel you towards. So I would say like, is there an area where it's bad? Not really, but a lot of the F sharp literature won't necessarily push you in the direction of performance, which is why I do what I do to kind of say like, okay, it's not like that's cool. Don't get me wrong. Like that domain modeling, love it. But if you need to go fast, you might need to design a little bit differently. And every shortcoming I've come across in the language, and they exist, right? That's a whole nother talk. You can get around them. So for example, F sharp tuples are reference types. If you allow the time, the compiler can again elide them so you don't see it, but there are also struct tuples. Reference, the F sharp record type is a reference type. It could also be made a struct by just adding struct to it. So it gives you all the levers to get that performance. It just isn't necessarily the default of the language. And I don't have a problem with that. Like I understand like the .NET runtime is a object-based runtime. It is like baked deep into the bones. And so, yeah, F sharp was built that way. But you can say like, yeah, that's nice and all, but like, seriously, I don't need that. Like I can just go raw structs, arrays, all that. You're probably not going to find a ton of literature on it. So you need to go look at C++ and their design patterns for being able to do it in F sharp.
Well, it's a good thing because people can go watch your YouTube channels. So
I'm hope to help. So if people have questions, like I'm just showing you what I'm doing. It might be a little different, but I like writing fast code, and F sharp makes it easy for me to do that.
All right. On that note, thank you so much, Matthew. That was an awesome talk. People loved it in the chat. Chet says he'll still love you. The tent is big enough for everyone. So you and Chet can kind of hug it out after this.
Okay.
So thank you so much. You're always welcome back. We'll talk to you later.
Love it. See you soon. Bye.